basically two guys, T and A, go jogging or like walking. T will move at b meters per second for a seconds, then rest for c seconds, and it goes over. A will do the same thing but for constants e, d, and f. E meters per second for d seconds, then rest for f seconds. And after x time has passed, who's gonna be further? Well, let's make a function distance, which calculates for b, a, c, or x, y, z, and a time x, what the distance of the run for these three constants will be. If we have this function, then the solution is obvious. We just compare the value of this function for the two different set of constants. And the way I do this function is I did it naively because x is smaller than or equal to 100, so I iterate over all of the seconds from 0, 1, x minus 1. And the way the phase of a walking and resting phase will look is there's a seconds of one activity, c seconds of the other activity. So if I'm at the ith second, which is something like this, then I just divide it by a plus c and look at the remainder. Because I cut off all of the complete cycles that have already been done, so I cut off this part. And after that, we'll have I looking like this, and we can see if I is smaller than A, so it's between 0, 1, 2, and A minus 1, it gives that remainder. Then I is in the running phase, so I increase the distance by B. Otherwise, I do nothing, I just increase I, and I go through all I from 0 to x minus 1. Yeah. I can show the code for this, it's still okay. Here's the distance function, it's not anything too weird. Yeah. In problem B, I'll make a new board for all of these, and then I hope it won't lag. Discard this last one. In problem B, we were given a string, and we had to decide whether it's a wonderful string. A string is wonderful if it has uppercase letters, lowercase letters, and all of the uppercase letters are pairwise distinct, and all of the lowercase letters are pairwise distinct. Here, I read in the string, I made two strings, one string lower and upper. I put all the uppercase letters in the upper string, the lowercase letters in the lower string. If either of the strings are empty, then the answer is no. Or if either of the strings have a repeating character, then the answer is no. And these are the things I'm checking here. So if upper is empty, then the answer is no. If lower is empty, the answer is no. And I made this check function, which all it does is sorts the string and sees if there are any adjacent characters that are the same. If two adjacent characters are the same, that means so if if a character appears multiple times, then in the sorted order they will be together. I just print yes or no accordingly. Let's look at C. I think there might be a much easier solution for C, but I did it with bit masks. Just need to make this big enough. Let's discard that. Just reading the problem. I think the problem statement for this was very poorly written, because they used alphabets when they meant characters. So we are given up to 15 strings of distinct characters. So basically we're given 15 bit sets of at most size 26. I'm going to represent these strings as numbers, and all of the bit positions are given a character. Let's do, this is 2, this is 4, this is 8, 60, A, B, C, D, E, etc. And if the string looks something like B, D, E, then it's gonna be, so each string can be represented as a bit mask. And the problem was, we had to choose a set of the 15 strings such that the number of characters that appear in exactly k of the strings is as big as possible. Well, with 15 we can just try all subsets. So I make a mask equal to 0 up to 2 to the 15th minus 1. And this mask will store all of the possible subsets of the strings. Let's say one subset looks like this. That means this subset includes the strings at position 0, 2, 3, and 5. Now we take the strings at positions 0, 2, 3, and 5, and we calculate the number of, so we have a frequency array of all the characters, and I go through each string and I calculate the number of characters in it. Or I mean, if there's an A in the first string, well, I increase the count of A by 1. After I've done this for all strings, I go through the count array and I check how many positions have exactly k in it. So this might be 5, 4, so A, B, C, D, and here you can see A appeared k times, B appeared k times, C appeared 5 times, D appeared 4 times. Let's say k was equal to 8, and then the answer for this subset will be 2, because there are 2 letters that appeared exactly k times. Here, if you haven't done any bit masking, then I guess this is an example of how to do it. I have a mask. I go through all the strings. I check if the string is in the mask. So if this string is in the current subset, then I'm checking. I go through all characters and I check if the character I'm checking is in the string. AI is stored as a bit mask of the different characters. If the JAVE bit of AI is turned on, that means that the JAVE character is in that string, so I increase the count of J. And at the end I look at the number of characters which appear exactly k times in the given subset of strings. And I print out the maximum of those. Okay, and finally moving on to problem D. D was a pretty interesting problem in my opinion. you don't really see square root complexities often in these types of contests. This was pretty difficult in my opinion. Given an array of integers of length n smaller than or equal to 2 times 10 to the 5th, I think, and all ai is also smaller than or equal to 2 times 10 to the 5th. And we had to find the number of triples I, j, k, where order matters, such that ai divided by aj equals ak. This means ai equals aj times ak. Takes a long time for, yeah. Okay, times ak. So basically we need to find the number of triples such, or we need to find all AIs, no, we need to find all pairs of numbers whose product also appears in the array, and we'll have to count how many times this appears. What we can do is we can first of all make a frequency array for the given array. So we count how many 1s appear in it, how many 2s appear in it, count how many n's appear in it. And after this we iterate over numbers 1 to n, and we look at all of the pairs of numbers that multiplied together give, so this is I, and we look at all of the divisors of I. Well, we can do that in big O of square root n, by going from j equal to 1, and we increase j until the square root of n. This works because the two numbers that multiply together give n. One of them will be smaller than the square root, the other will be bigger than the square root, except when it is the square root. Because when you divide the number by another number that's bigger than the square root, it cannot go into it more times than the square root, like by definition. So we get the number of pairs, not the number of pairs, but we get all distinct pairs a, b, such that a times b equals I. And when we have this, we increase the number by count a times count b times count I, because all of the positions that have a, all of the positions that have b, and all of the positions that have I can be used as a triple like this. And if a doesn't equal b, then we also we add this twice, because these are ordered pairs. So the for I, j, k, 2, 3, 3, and 3, 2, 3 count as two different answers. But if the two are equal, then we only add it once. Yeah. And then for problem E, I thought about it for a while. I thought I had this like n cubed solution, but it seems to work for some of the samples, but doesn't work for the large sample. So I don't know, I'll work on that later. Seems like a cool, weird knapsack problem. I hope you enjoyed the contest. I hope this video helped some people, and thanks for watching.